moving into solving systems of linear inequalities. This is going to be different than it was when we were solving systems of equations and we were just looking for an intersection point. These are going to have several solutions, and we're going to have to show it with a graph. So, solutions to a system of linear inequalities are, just like they were when we weren't doing a system, but we were just doing one, how do we describe the solutions of a linear inequality? As a what? Ordered pair. As an ordered pair. So we have any ordered pairs, and it will be pairs. There will be more than one. Any ordered pairs are considered solutions to the system if it makes all the inequalities true. It's going to make all of them true. You can't just satisfy one or the other. It has to satisfy all of the linear inequalities in the system. Mr. Conlon, could you go close those blinds, please? Thank you. Okay, so where would these be located on the graph? Where do you think we would find the solutions for a system? Okay, so when we do this, we're going to be looking for in the overlap shaded region, wherever all of them are shaded. In other words, we have to find the region that all of them have the same ordered pairs shaded. So in the overlap shaded region, or as Michaela said, on a solid boundary line. But we have to be careful, we have to be just a little bit more specific there. On a solid boundary line around the overlap. Or in other words, it has to be a border of the overlap. Okay, that's another way to state it. On a solid boundary line, I missed the word line here. On a solid boundary line that's around the overlap, or in other words, it kind of borders the overlap. Okay, so here's our system that we're going to solve. Y, as you guys can see it, y is greater than x minus 4, and it has to work together with y is less than or equal to negative 1 half x plus 2. When we are doing these, we're going to do them one at a time. You're going to do one graph completely before you start the other. So you go ahead and get this one ready to graph because you know what you need to do. You need to identify the slope, the y-intercept, you need to say what kind of a line it should be, and you need to say where it would be shaded. So go ahead and identify all of those things on your papers. And then see if you need to change my mind or I need to change yours. So go ahead, if you agree with me and you agree with yourself, I guess, go ahead and graph that boundary line. And also do the shading, okay, on that graph. Don't even worry about the other one yet. Don't care about the other one at the moment. We're only going to focus on this one. Make lots of points. We need really good boundary lines for these systems. Just go crazy. And when you're shading, shade lightly. And shade going in one direction. Take that pencil and kind of, take it and lay it on its side and shade with it. Okay? So shade lightly, don't make it too dark because we're going to be looking for overlap and we can't sometimes see it if we shade too dark right away. And again, I'll be shading with kind of like my line like this, but you guys can do it nicely with your pencils. Whoops, I shaded the wrong side, didn't I? That's not above, that's below. Okay, let's try for above.
The opposite direction.
Okay. Okay, and make sure you and I, everybody who looks at your graph can tell that boundary line is what? Dashed. Okay. And then go ahead and move on to the next one. Going to be on the same graph, but we're going to do the same things. Identify all the things that will help us make a good graph. Okay? So identify your slope, y-intercept. Should be a solid line or a dashed line, shaded above or shaded below. And what you got to kind of do when you're graphing that second one, you got to kind of just like try and pretend that other one isn't there. Like you have a clean graph and you're just graphing this one right now. Remember what I said, make lots of points. Actually, it's kind of good if you can, if the lines are going to intersect, it's kind of nice to see where are they going to intersect. When you're shading the second time, sometimes it's a good idea to take your pencil and go the opposite direction. So when you're shading the second one, maybe do it going the opposite direction that the other one was going. The other thing I oftentimes let students do, or if they want to do, is use colored pencils. Use one color for one equation and another color for the inequality, and then another color for the other one. But there's a little bit of a catch with that. Colored pencils don't erase as well if you make a mistake. Okay? But you can use colored pencils on these if you want instead of lead pencils for your shading part. Okay? Then what we look for is we don't have any more to graph, so we're going to look for the overlap region. So where's the overlap region? Appear to be. On your graph, you have mine? Is on the top, bottom, left, right? Where does it appear to be? To the left there. It's kind of like, yeah, there's this kind of triangular region there. So now what I want you to do is I want you to take your pencil, and in that overlap region, I want you to triple shade. I want you to give it, I want you to really define, showing that this is the solution region. I'm not saying you have to do it really dark, I'm just saying make it stand out, okay? So when you are shading, you're gonna, this is the overlap region, so we're just going to shade over it again, so that when somebody looks at your graph, they can say, oh, there's the solution region. I can clearly tell where the overlap is. So now, any ordered pair in that, what we just called triple shaded now, our overlap region, any ordered pair in there is considered a solution for this system. Where else could we possibly have some solutions for this system? What do you think, Riley?
On the solid boundary line?
Okay, the whole solid boundary line?
No, in the overlap region.
Just around the overlap region. So from here on up, right? From where they intersect, going that way. How about this one? How about the dash line?
No.
No, that one we can't count.
So,
How about the point of intersection?
Yes.
No, why not?
because the dash line goes
One of the lines is dashed and the other one is solid. So it's a solution for the solid one, but it's not a solution for the dashed one. And it has to be a solution for both of them. It has to make both of them true. So the point of intersection in this one would not be a solution. Any points on this dashed border right here would not be a solution. But the points on this part of the solid line that borders our overlap would be a solution, right? Okay, let's just do this in our notes because I want you to know that, I want you to realize that you should check sometimes. Some of you are just happy to get answers and don't check. I'm not saying you have to do check problems in your homework, but I want us to do them in our notes right now. So we're going to pick two different different ordered pairs that we think are solutions, and we're going to check them. So Riley, you're gonna pick the first one for us?
0, 0.
0, 0. Okay, can we pick 0, 0, class? Do you like his choice? Okay, let's just do that one first before we pick our other one. We're gonna pick 2 of them, but let's just do that one first. So we have y is, remember our my inequalities, greater than x minus 4. And we have to check it in the other one, y is less than or equal to negative 1/2 x. Plus 2. Hey, you put zeros in for both your x's and your y's? What happens in the first one? What's the statement that we get? Riley?
0 is greater than 0 minus 4.
And what is 0 minus 4? Negative 4. Is that true? Okay. So far it's looking like it might be going to check, but it has to check in both of them, doesn't it? So this is true. Okay, we're happy with that. That's true. Okay, now let's do this one.
Why'd you put a T there?
It's true.
Oh.
For the word true. Okay. Okay, what does this one end up? 0 is less than or equal to, what's half of 0?
2.
Or a negative half of 0? 0. What's 0 plus 2? 2, okay? True or false statement? Is 0 less than 2? Okay, so we get another true statement. So we could say this one checks, right? Okay? 0, 0 checks out. Okay, let's, you know what, I think it would be for the fun of it, how about we check one on that solid boundary line we think is a solution? Let's pick one from the solid boundary line, okay? Remember, can we use the intersection point? No, okay, so give me, Cole. Negative 2, 3. Okay, so that was one of the points used to make the line, so I think it should work, okay? So let's do negative 2, 3. That's the one we're checking now. So we have our y is greater than x minus 4, and our y is less than or equal to negative 1/2 x plus 2. Okay, go ahead and sub into those correctly. Remember, 3 is going in for the y's, and negative 2 is going in for the x. For that first one, did you get 3 is greater than negative 6? Is that true? Is 3 greater than negative 6?
Yes.
Okay. How about this one now then? What's negative 1/2 times negative 2?
1.
1. What's 1 plus 2? Is that true? Because it meets the equal to part, doesn't it? So this one's true also. So just like we thought, on a border that is solid, they're considered solutions also. Okay, so you do not have to show check problems, but I want you to know how to show check problems. And I think some of you need to spend more time showing check problems, especially on assessments, because you're making crazy mistakes, and it would lead you to going back and saying, wait a minute, something got wrong here. I didn't get a good answer. That's what happened in the last quiz when we were doing equations, systems of equations. So, any concerns before we go to the back side? Okay, on the top of the back side, I am going to tell you right now, you're going to have to do some studying in the book on your own. We are not going to graph any of these kind. We're not going to do any of these kind. But if your boundary lines turn out parallel, so you have these boundary lines and they're parallel. One might be solid, one might be dashed, they both might be solid, they both might be dashed, it doesn't matter, they're parallel. There can be ordered pair solutions. When we have equations that we're solving, systems of equations that we're solving, and we have parallel lines, can there be a solution? No, because what happens? They never intersect. So how can there be a solution for equations if they never intersect? But what are we looking for here? Are we looking for the lines to intersect?
No.
What are we looking for? Riley?
The shaded region.
The shaded regions to intersect. That's what we're looking for. We need those shaded regions to intersect. So there can be ordered pair solutions when there is what?
Parallel lines.
Overlap. Remember? Intersect here means overlap shading. Okay, let's just call it that. I don't think I gave you a big enough space, but let's overlap shading. Then there would be a solution. When there is no overlap, there's no solution. They don't have any points in common. They do not have any that they are sharing because they don't have the same shaded regions on top of each other. So there are 3 different possibilities of what can happen when you're working with parallel lines. You got these parallel lines, and when you are doing the shading, for one of them you shade above, the other one you shade below, and guess where the overlap shows up sometimes? In the runway, I call it, between the 2 parallel lines. So the whole graph looks shaded, but the overlap is right there between the runway, between the 2 lines. That would be our solution region. Would the parallel lines be included in the solution region?
If there is force.
Only if they're solid. Yeah, only the solid ones, right? Okay, what if you shade above, one of them above and the other one below, and they're going opposite directions from each other? Will there ever be any overlap?
No.
No. So then that would be a no solution one. But then there's also the time when you're shading for them, and one of them they both get shaded either above or below. And when that happens, there's going to be overlap. And the overlap is actually going to turn out to be the shaded region for one of the inequalities. You need to study this in the book. Okay, the book does a really good job with it. You guys take a look at it because you're going to have some of that in your homework. Okay? Let's go on to now our other part that we have to do today, which is set up our own system of linear inequalities and then graph it. So we have this party Alice is having. She is serving pepper jack cheese and cheddar cheese. She wants to have at least 2 pounds of each. Apparently she knows she's already going to eat 1 pound of each. And wants to spend at most $20. Pepper jack sells for $4 a pound and cheddar sells for $2 a pound. So again, when we're trying to set up our own, we always describe X and Y. What are the things that are going to change in this? Because that's what X and Y have to represent. What can change? Ian?
The pounds of, the pounds of pepper jack and pounds of cheddar.
Yeah, the pounds, how many pounds she buys can change. We already know how much they are. That isn't going to change. $4 a pound for pepper jack, $2 a pound for cheddar. So we're going to let X represent the pounds, with a pen, pounds of pepper jack. And would you look down on the graph below? Is that what I chose? Oh, good.
Yeah.
Okay. Pounds of pepper jack cheese. And then Y has to represent the other 1 pounds of cheddar cheese. Okay. Well, let's also make note of, she wants how much?
At least.
At least 2 pounds of each. At least 2 pounds of each. Okay, little hint, this one's going to have 3 inequalities in it. 3. It's going to be a busy graph. So if she wants at least 2 pounds of each, I'm going to help you out. I'm going to give you the first one. The pounds of pepper jack have to be greater than or equal to 2. Which one's 2 pounds? At least. Does that make sense? That's 2 pounds at least. So what would another one be? Y is greater than or equal to 2. I'm going to make mine a different color, stand out a little bit better here. Here's our second one. Well, remember, she also wants to spend some money. Okay, Riley. Oh, I'm sorry, can I call him Blaine, because you,
Yeah.
I'm calling you a lot. Blaine, what do you think?
Four X
4x
plus 2y is greater than or equal to 20.
plus 2y is greater than or equal to, is that what I heard? 20?
Yes.
Okay, well, Riley's gonna override you for some reason. Riley, what's the problem?
It should be, 4x plus 2y is less than or equal to 20.
They convince Blaine why?
Because in the problem it says she wants to spend at most $20.
At most. Here she'd be spending at least $20, wouldn't she? Okay, Blaine, can we convince you to change it? Okay, we're gonna change that to is less than or equal to. How much money is spent on pepper jack cheese? 4x. How much money altogether is spent on cheddar cheese? 2y. How much money she wants to spend? No more than $20. Okay, let's get ready to graph these. One at a time, remember? Okay, so let's take this one and let's say, what kind of a line do we have there? Anybody remember?
Vertical line.
That's a vertical line. When there are no y's in it, that's a vertical line. So we have a, let's write that. We have a, I wanted to change it to green. I will. Okay. We want it to be a vertical. Solid or dashed? Solid. Shaded. Above or below? How do you
Above.
shade above or below a vertical line?
You shade.
Greater than to this side.
Greater than would go this way and less than would go
No.
that way. Okay, so which way are we gonna go? We're gonna shade it right. Shade it right. Okay, we're gonna do that one before we even talk about the other two. Where's our first point go on the graph for a vertical line?
2
2.
on the x-axis.
On the x-axis. Oh, by the way, we gotta do some numbering on our graph here yet, don't we? Let's number our axes out. Okay, what's the x-axis going by? What's its scale? No,
0.5.
0.5, half a pound. Every grid line is a half a pound of pepper jack. What's the y-axis going by? Going by 1, okay. So, do we have to worry about that with a vertical line? No, what do? We just take we put our point at 2, we take our straight edge and we draw a, what kind of a line did we say? Vertical and solid or dashed? Solid. And does it need to extend down into quadrant 4? No, but can it keep going up this way? Sure can, okay? And we decided we're gonna shade to the right. So go ahead and shade that one lightly. And now we'll move to the next one, which is y is greater than or equal to 2. What kind of line is that? Horizontal line, okay. So this one's horizontal. And should it be dashed or solid? Solid. Can we shade above or below a horizontal line?
Yes.
Yeah. Should we shade above or below?
Above.
Above. And where will we start on the y-axis? At 2. Okay, so we will go put a point at 2 on the y-axis and have a solid horizontal line. Does that horizontal line need to extend back into quadrant 2? No? But can it keep going this way in quadrant 1? Yeah, it can it? And we're going to shade above, so now we're going to shade again, and boy, this is getting to be a really busy graph. Already, and we're not even done yet. Right now, there's only one part of the graph that isn't shaded, it's a little rectangle down in the corner, right? Yeah, okay. Now we need to get our last one ready to graph. So we have a couple of options. We can put it into graphing-friendly form, slope-intercept form, or we can find the x and y intercept and do it that way. What do you think? Do you think this would be a good x and y intercept one?
Yeah.
I think it looks like it might be. 4, 2, and 20, do they all seem like they like each other? Okay, let's do the x that way. So we're going to find the x-intercept first. To find the x-intercept, we put 0 in for y. So what we really have is 4x is less than or equal to 20, right? The y's are gone.
So this is the overlap.
So now we have 4x that has to be divided by 4 and 20 that has to be divided by 4. What is that? 5. So our y-intercept for this one is 5. I'm going to go put that on my graph. Now I need the x-intercept, or the y-intercept, excuse me, not the x. We just found the x. Now I need the y-intercept. What disappears when you're looking for the y-intercept? The x's. So I'm really going to be solving 2y is less than or equal to 20. So what's our y-intercept? 10. Okay. So even though there's an inequality symbol in there and everything, don't worry about that. We could replace with an equal sign, because all we're really doing right now is finding the x and the y-intercepts. So in reality, it might be probably a little less confusing if we actually did that, made these equal signs, because that's what we're finding. That's all we were doing in that. We were just finding the x and the y-intercepts. Now we go back to its standard form and we say, should this be a solid line or a dashed line? Should be solid. And should it be shaded above or below? Above. Is less than, is above?
Well.
Is less than, wouldn't that be below? Okay. So we get this, we already have our, I do anyway, have my intercepts graph, so I can now connect those two. Do I want to extend that line segment in either direction? No, I want to stop. I want it to be a line segment, not a ray.
No.
And I need to shade below. Is this like craziness or what?
This is pretty crazy.
Have you got like the busiest graph in the world?
It's beautiful.
Yeah, it is when you use colored pencils.
Ew. Depending on what colors you use.
Is this the overlap area? Or is
Okay,
it
now we have 3 of them.
3? So this is okay.
So we have to have, in reality, the whole thing ends up shaded right now, doesn't it?
Oh, that hurts.
Some of it is single shaded, some of it is double shaded, some of it is triple shaded. We're looking for the triple shaded.
Okay.
Where is it?
Oopsie.
Right in that little triangle.
Yeah, right in that little triangle. It's right here. Right here. So take your pencil now and quadruple shade it.
Yellow.
Well, yellow, yeah. I'm gonna do yellow. You're gonna.
Yes, thank you. That's the first time you used yellow.
Is it?
Oh boy.
There we go.
It's beautiful.
Looks like
Now, when you look at your graph, it better stand out that that triangle is the solution region.
Christina, which one is my shape?
Use my number 4 pencil, it's way just pencil.
There's number 4.
There's number 6.
It does.
This is the ground.
Looks like a Cool Ranch Dorito, like with the little specks.
That is.
Oh,
I'm hungry. Thanks for scale. I'm hungry.
Okay, I have a question for you. All of the points that are in that triangle count?
no.
Which ones do?
Every single one.
Every single one. Did it say she was only wanted to buy whole pounds of cheese? No. Can you buy parts of pounds of cheese?
Yeah.
Yeah. Okay. How about the borders around it?
Yep.
This triangle has 3 sides. Are all 3 sides of that triangle included in the solutions?
Yes.
Yes.
Why?
Because
they're
Because
all
they're all solid, aren't they? So anything inside and anything from here to here to here. How about question, how about these guys? This point of intersection right here. This point of intersection right here. This point of intersection right here. How about those guys?
Yes.
Well, I'm not racist, so yes.
Because they are intersecting on what? They're intersecting on solid lines. Both of the lines where that point of intersection where they meet, they are both solid. So those count also. So we're not going to take the time right now to give 6 possible combinations because we're out of time. But
That's not
when you give 6 possible combinations, you pick them out as ordered pairs first, but then how do you describe them? Okay, so-
X and Y.
What's this point of intersection right here? Can somebody tell me what this one is? 2, 6. 2, 6. So we would say 2 pounds of pepper jack cheese and 6 pounds of cheddar cheese is how we would state that. Okay? Okay, get that? Get out a sheet of loose leaf paper